we have two parallel conducting rods connected by a wire with a certain resistance R. We have within that a magnetic field that is into the board and a metal rod that is connecting the two. The magnetic field has a value of 1.5 teslas. The resistance is 2.0 ohms. We are going to push the rod to the right with a certain velocity. That velocity is going to be 5.0 meters per second. The length of the rod, or the distance between the two rods, is going to be equal to 25 centimeters. I want to know several things. A, what is the force we must apply to the rod in order to get it to move to the right? B, what is the power delivered by the force applied? And C, what is the power dissipated in the resistor? We actually went through something like this recently that was similar last time. We have this rod moving to the right in this magnetic field. So let's start there. We have our magnetic field. The rod is moving to the right. If the rod is moving to the right with some sort of velocity, this means that we have positive charges on this rod that are moving to the right, correct? We point our fingers in the direction of the velocity, curl our fingers in the direction of the magnetic field, our thumb points up. In other words, positive charges are going to collect on the top, negative charges are going to collect on the bottom. If you think about the force on a negative charge, it will be in the opposite direction. This will create an electric field, which looks like this. If we're moving at a constant velocity, this will create a constant electric field. If we look at a single positive charge on this rod, the forces on this rod will be what directions, Jenkins? Give me the forces and directions. We have a positive charge now moving to the right. I've offset it slightly so we can draw the free body.
So it's in the rod?
So it's in the rod, correct. So it's in the electric field, but it's also moving to the right in this magnetic field.
It'd be going into the board?
I want to know what is it.
Oh, on the positive charge.
Well, the positive charge is moving with the rod to the right.
There's a field going down.
There's an electric field going this way.
So, curl your fingers. Is that what you're looking
But that's
for?
the direction of the electric field. You're confusing two different things, okay?
Oh.
Right, because you're using the right-hand rule for the magnetic field, which is, or for the electric
Yeah.
field, which is confusing two different things.
It'd just be. I don't know.
That's okay. Mag up, no.
Lost.
We're missing stuff here. Potterell.
You have the electric force down,
Because
it's a positive charge, and it goes away from the positive charge to the top.
the electric field is defined by a positive charge. It's going to be repelled from the positive charges, attracted to the negative charges. Good. We have an electric force, which is down. We also have what else, Tyler?
I don't know.
Class, get out your right hand.
Magnetic force.
Point it. No, we're done with that.
All right.
Point it to the right in the direction of the velocity. Curl your fingers in the direction of the magnetic field. Your thumb is pointing what direction? Up. This is the direction of what?
Force.
Magnetic force. So we have a magnetic force which is pointing upward on this, right? If we sum the forces in the y direction on this charge, we get the magnetic force is up minus the electric force is equal to mass times the acceleration in the y direction. It's moving at a constant velocity, which means this will have reached equilibrium. So the positive charges, will they be moving up or down, class? No, neither is fine. Therefore, the acceleration in the y direction is going to be equal to 0. Therefore, the magnetic force is equal to the electric force. The equation we're going to use for the magnetic force, Yuchin.
QED sin theta.
Great, so we have from here, Q, V, B times the sine of theta. We're just working with the left-hand side for now. Charge is just the charge, V is the velocity, B the magnetic field, sine of the angle. This is the angle between the velocity and the magnetic field. What is the direction, or I'm sorry, what is the angle, class? 90 degrees in that particular case. It's going to be 90 degrees. Okay, so on the right, we need the equation for the electric field? Travis, I'm sorry, the electric force is Q times the electric field. Class, everyone brought charge to the party. Which means the electric field is equal to the velocity multiplied by the magnetic field. Okay, we have the electric field. The electric potential difference. In a constant electric field, which is what this is, a constant electric field, the equation for the electric potential difference in a constant electric field, Tim, is what? The order is irrelevant, but E times D, one other small piece.
Negative.
It's negative. This is for a constant electric field. We are really, at this point, only concerned about the magnitude of it, so we're just going to take the magnitude, which is going to be just equal to E times the D. So that's going to be the velocity times the magnetic field. Well, D is just going to be this whole piece right here, which has a length L, so L. This particular EMF has a specific name. What's it called, Michael? Gary. Miller. Motional EMF, the equation you brought up before. This is the motional EMF. Because this bar is moving to the right, this metal piece is moving to the right at a certain velocity, it will create a potential difference, which will cause a current to flow in this situation. So if you look at it, we have our magnetic field. We are pushing on it to the right. This force applied causes a magnetic force on positive charges, which is up. This is going to cause in our circuit here, a current, which is upward. We have a force applied to the right. We have a current upward. Get out your right hand, please. Point your fingers in the direction of the current. Curl your fingers in the direction of the magnetic field. Your thumb points, class.
Left.
To the left, this is the direction of the magnetic force. There is a magnetic force to the left, which makes it difficult to push this to the right. That's why it can move at a constant velocity, because it will actually cause an acceleration to the left, slowing it down. So what we're looking at here is we need to figure out this force applied. Now that we've drawn our free body diagram, Hamza, what should we do next? Sum the forces. We sum the forces in the x direction. We get that the force applied minus the magnetic force is equal to mass times the acceleration in the x direction. Class, what's the acceleration in the x direction?
0.
0. Because it's moving at constant velocity. In other words, the force applied is equal to the magnetic force. Bless you. What equation are we going to use for the magnetic force? Dorfstedt. For this, our current carrying wire. ILB sine theta, IL cross B. If we're trying to figure out the force applied, we need to figure out the magnetic force. The current, well, let's see. We don't know the current yet. We know L is just L defined there. The magnetic field we have times the sine of class. What's the angle between the current and the magnetic field?
90.
90 degrees, times the sine of 90. So we have an issue. In order to figure out the force applied, we need the current. How are we going to figure out the current in this circuit, Mr. Hutterell?
Use delta V equals IR.
We know electric potential difference equals current times resistance. Keep going.
Okay, so current is equal to times the difference of the resistance. And we have the equation for potential difference.
We just solved for the motional EMF, the electric potential difference, so it's the velocity times the magnetic field times the length divided by the resistance. I can't stress it enough. Class, is the delta on the electric potential difference important?
Yes.
Yes. Okay, so we come back to the force applied. The force applied then is equal to the current, the velocity times the magnetic field times the length, divided by R, the resistance, multiplied by L. This L is the same. I'm just drawing one cursive. I'll be consistent here. So the force applied then is equal to the velocity times the magnetic field squared times the length squared divided by the resistance. We have numbers for all those things. The velocity was 5. The magnetic field was 1.5, which we're going to square times the length, which is 25 centimeters, or 0.25 meters, which is also squared divided by the resistance, which is 2. Therefore, the force applied is equal to
0.3516.
with sig figs, we'll go 0.352, even though I think I had one thing with one sig fig that you can handle, it'll be okay. No, everything has 2, whatever. Okay, now the question is, what is, for part B, the power delivered by the force applied? Power delivered by the force applied. Minish, we have a couple of equations for power.
Current times potential.
Current times potential difference, but this has to do with not electric power, but rather mechanical power. So that will be actually what we're going to talk about when we get to part C, which is the power dissipated by the resistor. But we're talking mechanical power.
Force times velocity times cosine theta.
FV cosine theta. We have the force applied. We have the velocity. We have the angle between the two. The force applied is, let's do it this way. Force applied is V squared times L squared divided by R, the resistance, multiplied by the velocity times the cosine of class. What's the angle between the velocity and the force applied? 0. Cosine of 0, thank you class, is equal to 1. Therefore, the power delivered by the force applied is equal to velocity squared, magnetic field squared, the length squared divided by the resistance. 5.0 squared times 1.5 squared times length 0.25 squared divided by the resistance 2. The power delivered by the force applied. With sig figs, 1.76 watts, or at least 3 sig figs, even though we're on the 2 in the problem. Part C, the power dissipated by the resistor. We now have electric power. Nitish, go ahead.
Current times potential difference.
Okay, we have current times electric potential difference. Look, we have the current. Current is equal to the velocity times the magnetic field times the length divided by the resistance, multiplied by the electric potential difference, which is the velocity multiplied by the magnetic field times the length. Or look, hey, it's velocity squared, magnetic field squared, length squared divided by the resistance. I think we know that, 1.76 watts. In other words, the amount of energy we put into the system with the force applied is entirely dissipated by the resistor. Makes sense. All the energy we put in goes to